Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. Today we are going to discuss about the module Field Effect Transistor FET from the paper Semiconductor Materials and Devices. So the learning objectives of this module are: first, we will be discussing the junction field effect transistor, JFET, its basic structure. Second, the operation of JFET, that is basically N-channel. Thirdly, the IV characteristics of N-channel JFET. And lastly, we will also discuss about the theoretical characteristics of a JFET. So students, let us start with a basic introduction about the module. The modern era of semiconductor electronics was ushered in by the invention of bipolar transistors in 1948 by Barden, Brayton and Shockley at the Bell Telephone Laboratories. This device, along with its field effect counterpart, has had an enormous effect or impact on virtually every area of modern life. In this module, we will learn about the operation, the applications, and the fabrication of junction field effect transistors, JFET. The field effect transistors comes in several forms. In a junction FET called as JFET, the control gate voltage varies the depletion width of a reverse biased PN junction. A similar device results if the junction is replaced by a Schottky barrier, that is metal semiconductor FET called as MESFET. Alternatively, the metal gate electrode may be separated from the semiconductor by an insulator, metal insulator semiconductor FET called as MIS FET. So a common special case of this type uses an oxide layer as the insulator known as MOSFET. So we have found that two dominant features of a PN junction are the injection of minority carriers with a forward bias and a variation of the depletion width W with reverse bias. These two PN junction properties, they are used in two important types of transistors. The bipolar junction transistor BJT uses the injection of minority carriers across a forward biased junction, and the junction field effect transistor discussed in this module depends on the control of the junction depletion width under reverse bias. So the FET is a majority carrier device and is therefore called as a unipolar transistor. The BJT, on the other hand, operates by the injection and collection of minority carriers. Since the action of both the electrons and holes is important in this device, it is called as bipolar transistor. Like its bipolar counterpart, the FET is a three-terminal device in which the current through two terminals is controlled at the third. Unlike the BJT, however, field effect transistors, they are controlled by a voltage at the third terminal rather than by a current. So the history of BJTs and FETs is rather interesting. It was FET that was proposed first in 1930 by Lilienfeld, but he never got it to work because he did not fully appreciate the role of surface defects or surface states. In the process of trying to demonstrate experimentally, such as field effect transistors, Barden and Brattain somewhat serendipitously invented the first bipolar transistor. So the germanium point contact transistor. This major breakthrough was rapidly followed by Shockley's extension of the concept to the BJT. It was only much later, after the problem of surface states was resolved, by growing an oxide insulator on silicon, that was the first MOSFET was demonstrated in 1960 by Kang and Italia. Although the BJT reigned the supreme in the early days of semiconductor integrated electronics, it has been gradually supplanted the most applications by the silicon MOSFET. So the main reason is, unlike BJTs, the various types of FET, they are characterized by a high input impedance, since the control voltage is applied to a reverse biased or Schottky barrier or across an insulator. So these devices are particularly well studied for controlled switching between a conducting state and a non-conducting state, and are therefore useful in digital circuits. They are also suitable for integration of many devices on a single chip. So the field effect transistor FET, there are two kinds of it, that is junction FET and another one is metal oxide semiconductor FET. Now in this module we will be focusing on junction FET or JFET. And JFET is of depletion mode type, and there are N-channel JFET and P-channel JFET depending upon the type of the channel, which may be N-type or P-type respectively. So students, let us now discuss the structure of JFET. So as it is shown in this figure, where you can see the structure and the symbol of N-channel and P-channel JFET. Here the PN junctions restricts the cross-sectional area of the channel. So because the transition region of PN junction lacks only the mobile charge carrier, the width of the transition region depends upon the voltage applied to it. So the drain current varies according to the variation in gate source voltage. So N-channel JFET if the channel or the semiconductor bar is N-type, and P-channel JFET if the channel is of P-type. Let us now focus on N-channel JFET. Now thin bar of N-type channel or the semiconductor bar sandwiched between the two P plus regions, these are gate. Then the channel N-type is isolated from P plus regions gate by junction depletion regions. So the ohmic contacts are made at the two ends of the N channel for source and drain. Now we have three terminals: source, where there is the origin of carriers, that is if we apply negative potential with respect to the drain, electrons flow from source to drain. Second one is the drain, which act as the sink for charge carriers. And lastly is a gate, which is nothing but a rectifying junction with a channel. Operation of N-channel JFET. So now this figure shows the principal N-channel JFET structure where the device current is due to the flow of electrons from the source, that is N plus region, through the N-type layer called the N-channel into the N plus drain. The N-channel, it is sandwiched between the top and the bottom P plus layers, whose separation determines the channel thickness, and here it is denoted by 2A. The top and the bottom P plus layers creates PN junctions with the N-type channel. So the depletion layers associated with these junctions predominantly expands into the N layer because its doping level is much lower than the doping of the P plus regions. So the dotted line in this figure shows the edges of the depletion layers associated with the upper and the lower PN junctions. So it is the distance between the two depletion layers, not the separation between the PN junctions themselves, that is equal to electrically effective channel thickness. So now here the upper and the lower PN junctions, they are reverse biased, which increases the depletion layer widths, thereby reducing the channel thickness and thus reducing the current that can flow through the channel. So in the extreme case, the depletion layers extends over the whole thickness of the N-type layer, thereby reducing the electrically effective channel thickness to 0 and thus reducing the JFET current to 0. So this shows that the current can be controlled by the value of the negative voltage applied to the upper or lower P plus layers. Hence it is known as field effect transistor. Now here the voltage is applied between the gate and the source terminal, that is VGS, and since it is reverse biased, so VGS is less than equal to 0, whereas the voltage applied between the drain and the source terminal, which is denoted by VDS, is greater than equal to 0, making it forward biased. So with the application of the drain voltage, that is as VDS or VD greater than equal to 0, drain current flows. That is, there is some finite value of ID for VGS equal to 0. Now by applying VGS, the width channel varies, affecting the flow of charge carriers. Thus, ID is influenced by the application of electric field VGS. Practical structure of JFET. There is a thin N-type channel that is laid on a much thicker P-type substrate that provides mechanical strength as shown in this figure. So as there is a PN junction between the channel and the substrate and channel and gate, it provides a non-conducting walls to the channel as long as they are not forward biased by more than 0.5 volts. That is, when the channel is widest. The channel narrows when there is an increase in the reverse bias on either P region. So the output signal current is made to flow from the source and the drain by applying a DC reverse bias plus any signal voltages between the channel and the substrate. However, on the other hand, an electron current can easily flow through N plus junctions of source and drain. IV characteristics of JFET. So let us now discuss the current versus voltage characteristics of JFET step by step. That is the first case, the linear region. Now here, if a small Vd is applied, then a small Id, the drain current, flows, that is Id is approximately Vd by R0. That is Id increases linearly with increase in Vd. This is nothing but indicates that here the channel behaves as a resistor with resistance R0 and the depletion width remains almost constant across the entire channel. So let us now discuss another case, that is the pinch-off condition. When only a negative gate source voltage, that is VGS, is applied, leaving an open circuit at drain or connected to the source, it reverse biases the gate PN junction and so causes the transition region to widen, thus reducing the width of the channel. At a particular value of VGS, the gate widens through the P region on the other side, cutting off the channel. So the voltage at which it occurs is called as the pinch-off voltage Vp for a particular device, and at this value no current flows through the channel even if the drain source voltage is applied. So Vp is difficult to control in production, so it varies between the devices. So in this case, the channel near the drain, as shown in this figure, gets pinched off. That is, the source and the drain, they are isolated from each other by depletion. And the values of the current at this point are denoted by Vp and Ip. Let us now discuss the case 2, that is a saturation region. In this region, where the VDS is greater than VD saturation or Vp, then the drain current Id is constant for a given value of VGS. So the saturation in JFET refers to a limiting value of drift velocity. Now here the number of carriers that can be transferred through the channel per unit time is saturated and Id is constant equal to Id saturation. Now here, when Vd is greater than Vd saturation, Id is approximately equal to Id saturation and is independent of Vd or VDS. Now practically all additional voltage appears across the depletion region. Now let us discuss the case when there is a negative voltage applied, that is VGS is less than 0. So this figure shows the family of the curves when there is the finite VGS voltage applied, that is it is varying from VGS equal to 0 volt, minus 1 volt, minus 2 volts and so on. So here when a reverse bias VGS or VG is applied at the gate terminal, then the depletion region of P plus N junction becomes more wider, so width increases and cross-sectional area of the channel A is reduced. So what will happen because of this? For a smaller Vd or VDS, the channel resistance will be higher. So because the area available for the current flow reduces due to VGS. So Id reduces, its value reduces in comparison to the value of ID at 0 VG or VGS. So let us now summarize the IV characteristics of JFET. So this figure shows the current versus voltage, that is ID versus VDS, by varying the VGS from 0 to -4 volts is shown over here. So we have a linear region which we can say as the ohmic region, that is for VGS equal to 0 with increase in the small VDS, that is small depletion region, the current ID increases linearly and JFET act as the voltage controlled resistor. The second is a non-linear region. A non-linear region is indicated by the region between the linear and the saturation region. So for moderate VDS less than VD saturation, depletion width increases, average channel area decreases, hence the channel resistance increases. Thus, ID increases at a slower rate with VDS for a given VGS. So, next is a pinch-off region. It is nothing but a point where there is a pinch-off condition. VGS is made sufficiently negative of VDS equal to VD saturation such that the drain and the source, they are isolated by depletion width and constant ID flows due to injected charge carriers. Last region is your saturation region where VDS is greater than VD saturation, and we can say that VGS, the modulus of it, is greater than the modulus of VP. So here the drain current ID is constant with VDS for a given value of VGS. The theoretical characteristics of JFET. So here we will be deriving the IV relationship for a junction field effect transistor. So consider a JFET with VD less than VD saturation or VP and some VG is applied, that is VG is less than equal to 0. So the voltage drop across a small element dx as shown in this figure of the channel is dV equal to ID multiplied by dR equal to ID dx divided by 2q mu n multiplied by nd multiplied by z multiplied by a minus w as a function of x. So now taking the denominator to the left hand side, then we can say that ID dx equal to 2q mu n nd multiplied by z multiplied by a minus w as a function of x. This is multiplied by dV. Now here Wx is the width of the depletion region as shown in the above figure at the channel element x, and it is given by Wx equal to 2 epsilon s by qnd multiplied by Vbi minus Vg plus Vx. This is the whole to the power 1 by 2. This expression we have already evaluated in the case of metal oxide capacitors. that is MOS, metal oxide semiconductor capacitors. Here Vx is the voltage in the channel at a distance x from the source. So now differentiating above equation with respect to x, we get 2 multiplied by W as a function of x multiplied by dW by dV equal to 2 epsilon s by QND. Now rearranging the values for dV, we get dV equal to QND by epsilon s multiplied by W as a function of x multiplied by W. So students, if we put the value of dV in equation 4 and integrate from x equal to 0 to capital L and W equal to W1 to W2, where W1 is the depletion width on the source side and W2 on the drain side, we get ID to be equal to 2q square mu n nd square z by epsilon s L multiplied by integral W1 to W2 over AW minus W square multiplied by dW. So taking the LCM and rearranging the values, ID is equal to q square mu n nd square z by epsilon s L multiplied by A multiplied by W2 square minus W1 square minus 2 multiplied by W2 square minus W1 square divided by 3. Now we know that Vx is equal to Vd at Wx equal to W2 and Vx is equal to 0 at Wx equal to W1. Then using equation 5, we get W2 is equal to root of 2 epsilon s by QND multiplied by bracket VBI minus VG plus VD, and W1 is equal to root of 2 epsilon s by QND bracket VBI minus VG. Now therefore ID is equal to, by putting these values, we get q square mu n nd square z by epsilon s L multiplied by bracket 2a epsilon s divided by QND multiplied by bracket VBI minus VG plus VD minus 2a epsilon s by QND multiplied by VBI minus VG minus 2 by 3 multiplied by 2a epsilon s by QND multiplied by VBI minus VG plus VD the whole to the power 3 by 2 plus 2 by 3 multiplied by 2a epsilon s divided by QND multiplied by VBI minus VG to the power 3 by 2 square bracket close. Now therefore ID is equal to IP multiplied by VD by VP minus 2 by 3 multiplied by VBI minus VG plus VD by VP to the power 3 by 2 plus 2 by 3 multiplied by VBI minus VG divided by VP to the power 3 by 2. This is equation number 6. Now here we have let that IP to be equal to A cube q square mu n nd square z by epsilon s L as equation 7 and VP to be equal to q nd a square by 2 epsilon s as equation 8. So now The equation 6, which we have discussed earlier, describes the IV characteristics of JFET for VD varying between 0 and VD saturation. So now, if VD is greater than VD saturation, channel is pinched off. So ID is assumed to be independent of VD. So in summary, we have two different regions. That is, first is when VD is small, cross-sectional area of the channel is independent of VD, and IV is ohmic or linear. This is the linear region of operation. Second is when VD is greater than VD saturation. ID is approximately equal to ID saturation. And here the current is independent of VD. So this is known as the saturation region of operation. So now how can we represent these two regions mathematically? That is, for a linear region, we have VD or VDS less than VBI minus VG. So expanding the terms of the equation 6, which was previously discussed, having VD in binomial series and retaining first two terms, then we get ID to be approximately equal to IP by VP multiplied by square bracket 1 minus VBI minus VG divided by P to the power 1 by 2, square bracket close, multiplied by VD. So here, that is, ID is proportional to VD, that is directly proportional to VD for a given value of VG or VGS. Next is a saturation region. That is, to calculate ID in saturation region, put VD equal to VD saturation or VP equal to VD plus VBI minus VG. In the equation 6, we get ID equal to IP multiplied by square bracket VP plus VG minus VBI divided by VP minus 2 by 3 VP by VP to the power 3 by 2 plus 2 by 3 multiplied by VBI minus VG divided by VP to the power 3 by 2, square bracket close. It is equal to IP multiplied by 1 by 3 minus VBI minus VG by VP plus 2 by 3 VBI minus VG by VP to the power 3 by 2. So thus ID is independent of VD and it is almost constant. So let us now discuss the JFET small signal model at low frequency. So consider the equivalent circuit of N-channel JFET, that is, the change in the drain current due to change in the gate to source voltage VGS is given by delta ID equal to Gm multiplied by delta VGS, where Gm is the transconductance factor as shown in this figure. The drain resistance is given by RD equal to delta VGS by delta ID at a constant VD S. So, the transconductance is the reciprocal of the drain resistance, which is nothing but that Gm equal to delta ID by delta VGS at constant VDS, which is equal to, that is taking the partial derivative of ID with respect to VGS at constant VDS equal to IP by Vp multiplied by 1 minus VBI minus VG by Vp to the power half. It is equal to 2q mu n nd multiplied by Z multiplied by A divided by L. This is multiplied by 1 minus VBI minus VG by Vp to the power 1 by 2. So now Gm in saturation region, it is equal to Gd in linear region. Now what is Gd? Gd is nothing but the partial derivative of ID with respect to VDS or VD at constant VGS or VG. So it is equal to IP by Vp multiplied by 1 minus VBI minus VG by Vp to the power 1 by 2. So students, let us summarize what we have learnt in this module. First, we discuss about the junction field effect transistors. Secondly, we discussed the practical structure of JFET. Third, the operation of N-channel JFET was discussed. Next, we also discussed the IV characteristics of N-channel JFET. Then we also discussed about the theoretical characteristics of a JFET. Lastly, the JFET small signal model, that is at low frequency, was discussed. Thank you.